We have just seen the fundamental idea of variational inference, maximizing the elbow instead of the likelihood. But we have not talked yet about neural networks. Neural networks can be used inside the variational inference framework in order to model the different probability distributions. So first, we need to model the probability p theta of x given z. We model this distribution with a Gaussian distribution whose parameters, the mean and the covariance matrix, are determined by a neural network parameterized by the weights and biases theta, which takes z as input. More precisely, we have z, which is a latent variable at the bottom of the network, and the top of the network produces mu of z theta and sigma of v theta, which are respectively the mean of the Gaussian distribution of x given z and the covariance matrix of the Gaussian distribution of x given z. Note that the output of the network is not a precise value for x, but rather the distribution of x given z. All in all, we have simply chosen a Gaussian distribution for the law of x given z, and we model the parameters of this distribution by a neural network whose weights and biases are denoted by theta. Similarly, we model the probability q lambda of z given x by a Gaussian distribution whose parameters are estimated by a neural network parameterized by the biases and the weights denoted by lambda. So lambda here stands for the parameters of the network that takes x as input and that produces a distribution for z given x. More precisely, this network takes x as input and produces mu of x lambda and sigma of x lambda, which are respectively the mean and the covariance matrix of the distribution of z given x, where again, lambda is a set of parameters of the network. This network takes x as input and produces parameters for the distribution of z given x, and the network we've seen before takes z as input and produces parameters for the distribution of x given z. So we can quite logically combine these two networks by considering first a network that takes x as input and produces a distribution for z given x. Then we can generate z and consider the network that takes z as input and produces a distribution for x given z. The overall architecture is depicted on the left. The network at the bottom is called the encoder. It takes x as input and produces a distribution for the latent variable z given x. The network at the top is called the decoder. It takes the latent variable z as input and produces a distribution for x given z. The overall architecture is called an autoencoder. Here, the networks are parameterized by lambda and theta respectively, and each network is responsible for generating a conditional distribution, either q lambda of z given x or p theta of x given z. We can just cast these neural networks into the optimization framework that we have previously seen. This corresponds to first maximizing in lambda the elbow, then updating lambda, then optimizing the elbow in theta, then updating theta, and repeat the process. One problem with this approach using neural network is the fact that it is too time-consuming because each maximization requires to optimize a neural network. Indeed, the first step corresponding to maximizing the elbow with respect to lambda is equivalent to optimizing the neural network at the bottom. So each step of the optimization process corresponds to optimizing a neural network. The encoder at the first step of any iteration or the decoder at the second step of any iteration. Optimizing one large neural network is complicated enough. Optimizing jointly two neural networks is impossible. The procedure we consider here is related to coordinate gradient descent because we have a function, the elbow, which depends on lambda and theta, and each operation corresponds to optimizing either in lambda or in theta. So this procedure is nothing but cycling through the parameters lambda and theta. We could instead use another optimization technique. This is what we are going to do by replacing this procedure by a stochastic gradient descent approach.